All right, let's do two practice problems for growth and decay differential equations. So the first one says that you have a bank account earning interest continuously at a rate of 5% of the current balance per year. So that is a rate proportional to the current amount, which means you must assume that this is a growth and decay diffie-q. Then they're telling you that the initial deposit is $1,000 and no other deposits or withdrawals are made. Question is, how much money will the investor have in 17 years? This is really just a pre-calculus problem that we're looking at through a calculus lens. So the differential equation that we could write is we have D, and then say we call it our bank account. So dB dt, so our bank account changes with respect to time at a rate that is 5% of our current balance. Now I could go through separate, integrate, and solve, but what I learned already on the prior video is that I know that my bank account will equal the initial value times e raised to my constant of proportionality times t. And they're telling me that my initial value is 1,000, so I have b equals 1,000 e to the 0.05 t, and they're asking me how much is left in 17 years. So I can just plug in a 17 here, and when I put this in my calculator, I can get my answer, which is $2,339.65. And of course, I rounded this to 2 decimal places because it's money. Typically, we'd go 3 decimal places. My next problem deals with population growth. We're being told that population of a country is growing at a rate proportional to its population. So that should ring a bell in your head that says, okay, this is a differential equation that is based on growth and decay. So my diffie-q would be the population is changing with respect to time at a rate proportional to the current population. And then they tell us that the growth rate is 4% of the current population. So I put in a 0.04 here. So the question then is, how long will it take for the population to double? Well, let's go ahead and convert this to an equation. So P equals my initial population times e raised to the 0.04 t. And then doubling time is found when my ending value is twice my initial value. So I have 2a equals a e to the 0.04 t. And of course, I can divide both sides of this equation by a to get 2 equals e to the 0.04 t. And I could do this in my calculator, but I think I'll go ahead and practice working with natural logs. So I can log both sides or take the natural log of both sides of the equation. And I get the natural log of 2 equals, and then of course I've composed inverses here. So I'm left with 0.04 t. So t equals the natural log of 2 divided by 0.04, that will be my doubling time. And when I plug that into my calculator, I find out it is approximately 17.329 years.